we'll see how it goes. Okay, so let's see. So can everybody hear me good? Okay,
yes,
right.
it is fine.
Okay, all right. So yeah, here's a brief outline of my talk. So I'm going to talk a little bit about stellar graveyard, and then I'm going to talk about a type of neutron stars. I'll talk a little bit about pulsars, magnetars, millisecond pulsars, and I'll also talk about how we can use various pulsars to form the pulsar timing arrays, and what an interstellar medium is, and how can we study it using the pulsars, and of course, a discussion. So, stellar graveyard. So, to give you a little background, most of the stars in the universe, they die. Now, why does a star die? So, most of these stars, they begin with hydrogen, and over time, there's a nuclear fusion which forms helium. Now, the main governing factor in the lifespan of any star is the mass of the star. So if a star is really massive, so a star can collapse onto itself if there's nothing to stop it. So what helps it from from collapsing is the fusion process, because it releases tremendous amount of energy. But then fusion can go on only to a certain extent. So as I said, depending on the mass of a star, it can die in various ways. So to begin with, Sun. Sun is a low mass star, and it has mass of about 2 times 10 to the 30 kg. Now, Sun is considered actually a low mass star. So what will happen is, over time, in a few billion years, so the fusion process would stop, and because there would not be enough pressure for the fusion to go any more forward, and because there's no more fusion going, there's nothing stopping the core from collapsing. And so the core will collapse and the outer layer will expand, and it will become, first of all, it will become a red giant, and eventually it will become a planetary nebula. So the image on the very I don't think I can use my cursor here. Yeah, so the image on the very left side here is of a white dwarf. So white dwarf is formed when the core collapses, and it's actually supported by the electron degeneration pressure. So it's very hot, and this is what will happen to the sun. In the middle, you have neutron star. So if the mass of the star is in the range of, let's say like between 8 to like approximately 30 solar mass, the core, actually the star will go through something called a supernovae explosion, and that's true actually even for the black holes too. So any star having mass, I think more than 8 solar mass, will likely undergo supernova explosion. And what happens in supernova explosion, the interior, the core collapses and forms something more compact, and the outer layer actually explodes. Unlike white dwarf, it does not slowly expand, it actually like explodes. So it's very, very bright phenomenon. And it can form either a neutron star or a black hole, again depending on the mass of the star. So if it's like between 8 to 30 solar mass, it will be a neutron star, and if it's even higher, it will be a black hole. So this is what I call the stellar graveyard, and today the focus of my talk is neutron stars. So in this picture, what you're seeing and what you're looking at is Jocelyn Bell. She was the first person who discovered these neutron stars. The idea of neutron star was first proposed by Walter Baade and Fritz Zwicky in 1934. So neutrons were actually discovered, I think, somewhere in early 90s. And after their discovery, these two theorists, they figured that there must be some kind of star which is only made up of neutrons. And in 1967, which is almost about like 34 years later, Jocelyn Bell, when she was a grad student at the Bell Labs, what she found was, so she was actually looking at this data, and what she found was that every day she was finding these periodic pulses in her data. And this is what you're seeing in the picture on the left side. So what she also noticed that these pulses are actually 4 minutes coming earlier every day, which is the sidereal delay. And that's suggesting that the source is not in the solar system, it's coming somewhere from somewhere else. So as we today know it, these sources are the pulsars, and this discovery was given the Nobel Prize in 1974. And another big discovery that happened after the discovery of pulsars was the decay of gravitational waves. So I'll talk about it a little bit later. But in 1993, that was also given a Nobel Prize. So far, what I want to emphasize is the discovery of neutron star. All that may seem like, oh, we found a new source, but it just opened a big field of research. And so many people have their PhDs going on a neutron star, and we know there are like so many types of neutron stars. So this is a huge field and very interesting. So I want to talk a little bit about neutron star interior. What are these sources? So neutron star mass ranges from about 1.2 to 2.1 solar mass. Now let me tell you, it's not easy to measure mass of a neutron star. These sources are very tiny, okay? The radius, as you can see, is only 10 kilometers. And they are not in our neighborhood, right? They are not like, oh, here's the sun. They are like really far away from us at some like parsecs of distance. And the density of these sources is just, so as I said, they're very dense, is about 10 to 15 gram per centimeter cube. And the reason why they're still holding on to each other is by the degenerate pressure of neutrons. So for those of you who don't know the degenerate pressure, is basically Pauli's exclusion principle. So neutrons are actually fermions, and the principle says no two neutron star, no two fermions actually can be in the same state. So what that does is it constrains how many neutrons can be inside a place. It puts a constraint on the size of the source, and this causes a pressure which holds on to this star. So if you look on the right here, it's kind of trying to show you the different density we have inside a neutron star. So neutron stars, as I said, they're very compact. So if you look at the outer crust, so neutron star, depending on where you are, the density kind of varies. The deepest core of the neutron star have a density of about 10 to 18. Excuse me. To be honest, it's very hard to determine what the true density is, because it's like, okay, so to give you an idea, it's like, think of gas. Okay, so when we think of any material, actually, you want to understand what the temperature is, what the density is, what the pressure is, and that's called the equation of state. Given how compact these sources are, and like, it's very hard for us to determine the true equation of state for these sources, and it's an ongoing field of research. But this is our current understanding. So you can see that the innermost core has density of about 10 to 18 grams per centimeter cube. Now, to give you a perspective, it's basically, if you take a spoonful of neutron star, would be equivalent to a whole gigantic mountain maybe on the earth. So it's really dense. And another interesting aspect of neutron star is that, so I talked about white dwarf, there's neutron star and black hole. Neutron star are the most exotic sources just before black hole, because at least you can see them. Black holes, you can't even see them. You only see the light outside them. So anyways, so neutron star interior is very complex, and they're very dense. I think that's the message I'm trying to give away. So how do we see them? So the first way, as Jocelyn By discovered, she found pulsars. Now, reasons we call some neutron stars pulsar is because they are pulsating. So this image on the right, what you're seeing, so the blue ball is the pulsar. These pulsars, they have, or neutron stars, they have very high magnetic field, and it's actually bipolar. So you can see the magnetic field is coming from two opposite axes, and it's rotating. And whenever this beam is pointing towards you, you see a pulse. So that's what the lower figure is showing you. Like, so the pulsar is rotating, and it's like you take a torch in your hand and you keep rotating. So the moment the torch points towards you, that's where you take the pulse, and that's why it's called pulsars. So pulsars are basically rotating neutron stars, and another main reason why you're seeing a pulse is because the rotation axis and the magnetic field axis, they are not aligned. They can be aligned in cases of some pulsars, but in most of the cases they are not. And it's like, how do I say it? Okay, so imagine there's a dancer holding a torch, at a certain angle. Now, the rotation axis is different, and the hand is basically the magnetic axis. So it's as you're dancing, you'll see the pulse whenever it's pointing towards us. So that's where the pulse emission comes from. And the emission also across the magnetic axis, it's beamed. It's not all over spread out, and we'll talk a little more about it. And the period range have been found from few milliseconds to 24.5 seconds. So pulsars are basically excellent time tracking machines. So like, I mean, now we have like atomic clocks which give you very, very precise time, but pulsars are very, very good sources for that. So the emission mechanism. So the blue dot here, or more like circle, is a neutron star, and the green line is the magnetic axis. Now magnetic field, so it goes from one pole and it closes at another pole. So you have two kinds of field lines. You have the open field lines and you have the closed field lines. Now what happens is a charged particle from the surface of the magnetar, they move along these magnetic field lines. And because the magnetic field is so high, it's of the order of 10 to 12 Gauss, what happens is these charged particles, they zip around it. So are you guys familiar with cyclotron emission? Basically, you have magnetic field and a charged particle rotates. So this is an advanced version. It's called synchrotron. So where the magnetic field is very, very high and the charged particle gets accelerated and it radiates. So this is the radiation we see in the radio. And another important thing for pulsars is that because these pulsars are rotating very, very fast, like, they can go up to milliseconds. So these charged particles, they're also co-rotating with the pulsar. Now, as you keep going away and away from the surface of the neutron star, the velocity also increases because the velocity is omega times r. So omega is your angular speed. The angular speed of the pulsar is the same, but if you move away, if you go from a larger distance, it's moving at a faster speed. And that's where we reach something called as a light cylinder. So if you guys have any questions so far, let me know if I'm going too fast. Any questions? Okay. So the energy is radiated is because it's like a dynamo is rotating. So because it's the neutron star has a very high magnetic field and it's rotating so fast, so it radiates this energy in the form of kinetic energy, and then the poles are also radiating it. So what happens is, as it's radiating away energy, its period reduces over time, and that's something we measure observationally. So this is a very simple emission mechanism. To be honest, we scientists are still trying to figure out the exact mechanism, and this is only for the radio. The way you see, pulsars can actually be observed from a wide range of electromagnetic spectrum. So there it is. So electromagnetic spectrum, it goes from very low frequencies such as the radio waves all the way to the gamma rays. And we have so many radio telescopes. So I've put like lots of pictures. So there's the Arecibo, which used to be a very big dish. Now we have FAST, which is I don't know how big it is, but it's in China, and I think it's at least 300-meter dish. So it's a very big radio dish. Next we have is the VLA. So this is based in New Mexico. That's the state where I am in right now, actually. And it's got 27 dishes. And it can be used for imaging. It can be used for pulsars. Then there's a GMRD. That's where you guys are. And there's the Parkes telescope, which is in Australia. And right now for my work, I use the DSN, which is the Deep Space Network of NASA. So it's mostly meant for observing all the space missions of NASA. But what we do is whenever they have these empty time slots, we schedule our observations using the DSN. And so DSN has three main stations, I should say. So one is in California, which is in US. One is in Spain, and another one is in Australia. So depending on where we get the time allocation, we schedule our observations. And next in the series, we have NICER telescope and new stars. So these are X-ray. So pulsars, as I was saying, they emit from a wide range of frequencies. And so we observe them in radio. At least they were first discovered in radio, but later on they were also found to emit X-rays. And new star played a big role in understanding how these sources work. And right now, the telescope NICER, so this NICER is actually installed on the International Space Station. And so I use this for my work. And what we use it for studying low energy X-ray emission from neutron stars. And hopefully this will help us investigate what the equation of state is for a neutron star. And we also have the Fermi telescope, which is a great telescope. It detects all kinds of emissions from these neutron stars. So this is kind of an overview how these sources are being studied. So talking about subclass of neutron stars. So I talked about pulsars already, and those are mostly radio powered pulsars, because they're rotating and you have this emission coming out of their poles, which is mostly emitting in the radio. The figure on the right, I think that's a very important figure. So it's got two axes. The y-axis is the period derivative, which is showing the change in the period. The x-axis is the period. Now you can see there are three clusters. On the very left bottom, you can see there are these red, red, they're green dots, but these are circled by these red circles. In the middle, you're seeing these green dots. And on the very top right, you're seeing these blue stars. So let's start with the one in the middle. So the one in the middle are actually called as normal pulsars, because they have a period range of few from like tens of hundreds of milliseconds to a few seconds. So these are basically isolated normal pulsars where the period decays over some time and the values are not very extreme. Next, we have something called as a millisecond pulsar. And as the name goes, millisecond pulsar, these pulsars have period of the order of milliseconds, which is like really, so they are rotating like 1,000 times in 1 second. So that's like sometimes even the blenders you use for making coffee, or I don't know, whatever you're grinding, even they don't rotate as fast. So millisecond pulsars are really, really, really rotating very, very fast. And next we have something called as a magnetars. And I'll be talking more in the detail about these sources. So magnetars, they have high period. So the period ranges from like 1 to 10 seconds, but they also have very high period derivative. The period is decaying very slowly. Actually, sorry, it's decaying very fast. And in case of the millisecond pulsars, the period is decaying very slowly. So this plot is basically showing you the distribution of neutron star based on the period we measure. And I'm going to emphasize this. There might be many more neutron stars which we don't even see, because in order for us to see a neutron star, it needs to point towards us. And depending on how we see it, what kind of energetics it has, they are like all these types. So far, more than 2,700 neutron stars have, or I should say pulsars have been discovered. And I'm sure there are many more, which we would never even see. So next in the line, we have pulsar binaries. So millisecond pulsars, a majority of them tend to come in a binary system. And not just millisecond pulsar, there are also the X-ray binaries. So the X-ray binaries, what happens is, so you have a compact source. It can be actually a white dwarf, it can be a neutron star or a black hole. And it has another a companion from which this compact source actually somehow reaches a certain distance that it can start accreting material from the another low mass source, and that's how it emits in X-ray. That's why the name was X-rays. So anyways, so these are the various subclasses of neutron star, and if you try to dig deeper into it, you may find many more also. All right, so magnetars. So the quality of magnetars is they are very, very highly magnetic field. So for normal pulsars, the magnetic field is only like 10 raised to like 12 Gauss, which is itself very, very high. But for magnetars, it's even higher. And this magnetic field plays a very crucial role. So on the image here on the right side, so what you're seeing is this is not a real image, this is an artistic impression. But what it is showing is from magnetars, you see these very large X-ray bursts. And what we think is what's happening is, so you have this crust of a neutron star. And what happens is that because of very high magnetic field, there are these field lines. The crust sometimes just gets distorted, and you see these plumes of energies, and mostly you see this in X-ray. As I mentioned earlier, the period of these magnetars is in the range of 1 to 10 seconds, and so far there are only 30 known magnetars, and this is a very, very active field of research. So this is something I work on, and I've not put this information on the slides, but so right now I'm working on. So right now I'm working on like two. Okay, so recently there was a magnetar discovered in April, I think. So it was discovered in April, and we are trying to find what is the emission from this magnetar, and it varies so fast. These magnetars, the time scale of variation is like from few seconds to months, and the pulse profile from these magnetars changes. Like they have like a lot of varying features. So yeah, that's the story of magnetars. Now we have millisecond pulsars. So millisecond pulsars are very, very interesting in a sense. So these are old pulsars. So what happens is you have some pulsar, which neutron star, which emitted, and okay, so the period decays over a certain time. But what happens? Let's say if this is in a binary system, and it ends up accreting from its neighbor, so it spins up because it's getting all this energy, all this material from its neighbor. It starts spinning up, so that makes it rotate faster. And another thing that happens is the magnetic field from the accretion of material from another star, the magnetic field is also gets lower. So the period of millisecond pulsars decays very, very slowly. So these are very stable in period, unlike other categories. And that's why they play a very crucial role in something called as pulsar timing array, and I'll be talking about that in more. So there are, I think, more than about 200 millisecond pulsars, and most of them, as I said, they are found in binary system. Not all of them, some of them escape, and sometimes, like they can be they might end up interacting with another system, so sometimes they're isolated. And most of these millisecond pulsars, they are found in globular cluster. So globular clusters are these star clusters which are very compact, and they have a very high density of stars. So if you have a very high density of stars, you're more likely to have binary systems. And if you have binary systems with high mass stars, you can very likely have a millisecond pulsars. So what can we do with these pulsars? So pulsars are, as I said, they have very, very precise clock. So you can use that very precise period of this pulsar to study various aspects. So one thing that it's being used is for gravitational waves. And another aspect that it's being used for is how to explore the interstellar medium. So gravitational waves, I'm going to talk a little bit about it. It's just basically these are these ripples in the space-time which are caused by accelerating mass particles. These were first theorized by Einstein, and LIGO first discovered them in 2017. Actually, 2015 they discovered them. 2017 they got a Nobel Prize for this. So it was a big, big, big discovery in the field of astronomy, or in science in general, because we didn't even know if these waves existed. So here's a big spectrum. You guys don't need to get into too much detail. All I'm trying to say here is that just like you have electromagnetic spectrum, where you have, waves with very low frequencies and high frequencies, the same applies to gravitational waves. It's basically like a whole another window. And depending on what kind of system you have, so LIGO operates in the range of high frequency gravitational waves. Whereas, so high frequency gravitational waves are emitted by stellar mass black holes. So black holes can be of mainly of like two types. They can be stellar mass, that's the kind of black holes are abundant in our galaxy. And there can be supermassive black holes, and there's only one supermassive black hole that we know of at the center of our galaxy. But universe is huge, and most of the galaxies, they have a massive supermassive black hole at their center. And if there are two such, so here in this picture you're seeing there are these two big galaxies. This is again an artistic impression. These galaxies harbor a massive supermassive black hole at their center. And when these two galaxies, they collide, and somehow, okay, this is a whole very complicated process. Somehow, believe me that these two black holes, they come together. And these black holes, the mass of these black holes can be from million to billion times mass of sun. Sun itself is very massive. Imagine something being so massive, and they come together and they form a binary system. And if they form a binary system, these black holes, they revolve around one another. They form a very compact binary system. And over time, we expect the black holes, they come together and they eventually merge, and they emit gravitational waves. Now, these kind of gravitational waves, they would not be detected by LIGO, because LIGO works on high frequency, and these systems will emit something called as low frequency, and those will actually be detected by the pulsar timing arrays. So this is where pulsars come into the picture again. And you might wonder, how can a pulsar detect gravitational waves? So this is a very cool story. So think of it as, so on the picture here on the right, here's the Earth, our favorite planet. All these dots here on the fabric of space-time, they are neutron stars. They are basically pulsars. And what happens is, so when there's a gravitational wave, this is what, okay. So when there's a gravitational wave, what it does is squeezes and it compresses the space-time, right? So there's a, let's say there's far, far away, there is some binary system, okay, binary supermassive black hole system. It has collapsed, it has emitted, or it's coalescing, or it's like, the orbit is decaying. That's emitting these gravitational waves. These gravitational waves, they travel through the space-time. And what happens is, what they do, they affect the pulsar arrival time. So you have all these pulsars in one direction, right? So at some point, the phase time gets stretched. So when the distance between the pulsar and the Earth gets stretched, we would see that the pulse has delayed, and it can get squeezed. So we would see that the pulse time has arrived earlier. So what this pulsar timing array do, they are basically a network of pulsars. And in this case, they use only millisecond pulsars because they are very, very stable in time. So when they detect a change in the pulse arrival time, like when the pulse from the pulsar's arrival, oh, it has arrived earlier, oh, it has arrived later. And when they look for this change, and not just from one direction, like there can be a network of pulsars. So they would all experience the same delay or same earlier, the same stretching or pulling. So this way, when you correlate it between different sources, you can actually tell if there's a gravitational wave or not. And this is the whole story of pulsar timing array. I mean, this is way more complicated than that, but I'm just trying to give you a broader picture of what really happens here. So now moving on to interstellar medium, you may wonder this transition is so abrupt. So I'll tell you why. The story of pulsar timing array, where I said, you measure the delay in the pulse arrival time, or if the pulse has arrived earlier, it's not that quite straightforward. And the reason being is because we have this very interesting medium between these pulsars and us, and we call this interstellar medium. Interstellar medium is actually medium between all the stars, basically it's not constant to the solar system. Actually, it's anything beyond solar system, and whatever is between the stars, that's what the interstellar medium is. Now this interstellar medium is not empty, okay? It's got something called as ionized plasma. It's also magnetized, and this plasma is not homogeneous. It's got clumps. It's got somewhere it's dense, somewhere it's rare, and this electron density, it's fluctuating. So this is a very, very crazy place. Although it seems like, oh, there's nothing there, but a lot is happening there. And because there are all these fluctuations happening, what happens is the refractive index of the medium also has a lot of irregularity over time. And as a result of this, we see a lot of effect when we study pulsars. So that's why interstellar medium affects the pulsars, and that's why pulsar, because they get affected, we can use the pulsars to study the interstellar medium. So few observable effects are the dispersion. So dispersion in very simple terms is you have a prism, you pass a light through this, the light splits into 7 colors. And the reason being, the prism has all the components of light, they have dependence on the refractive index. So every component, when it travels to the prism, it travels at a different speed. Similar exact thing happens when light comes from a pulsar. So the figure here on the right may seem a little complicated. So let me simplify. Let's look at the bottom panel first, okay? And the y-axis is the frequency. The x-axis is the pulse phase. So as I said, these pulses are periodic, right? So imagine you have a pulse coming, but its pulse has got multiple components of frequencies. So it gets delayed. The lower frequencies, they get delayed as compared to higher frequencies. And this is called as the dispersion. And this is the first thing. So when astronomers, they discover a pulsar, this is the first thing they have to correct for is the dispersion delay. Because pulsars are very weak signals. And if you do not, so what they do is, so, let's say the period of a pulsar is 1 second, okay? And they fold the data. So let's say they observe it for like 10 minutes. So they would have like, period is 1 second, I said, right? So 10 minutes times 60 is how much? 600 seconds. So they have to fold it. So they take 1 second data and then they keep folding it. And then they try to detect a very bright pulse, and then we name it as pulsar. And that's how they discover a pulsar. But let's say they do not account for this dispersion. You will not see this very nice bright pulse as you're seeing on the top panel here. It will all get smeared out. So dispersion is a very, very important phenomenon which needs to be corrected. Now, if you go forward, I want to explain something more complicated phenomena, just to give you an idea. So here is your pulsar on the left side. It's emitting these radiations, okay? And here is the observer. Hello? Okay. Sorry, I don't know, something happened.
Shreya Hirve has a question.
Oh,
what do you
okay,
mean
yeah.
by folding?
Okay, very good question. So what I mean is, let's say you take, as I said, okay, so let's say a pulsar has a period of 1 second, okay? And you observe it, let's say, for 10 minutes. So you got total 600 seconds. So what we do is we take a chunk, we divide the data into 1 second chunk, and we all add them together only in 1 second. That's what I mean by folding. So let's say you have a signal which is very, very weak, but you will have 600 chunks of that, right? So if you add them all together, your signal, the signal to noise ratio will improve. The signal will appear brighter. Does that answer your question?
Yes.
All right, sounds good. So yeah, folding is very important when you are searching for pulsars, or when you're studying pulsars in general. We fold it all the time, I guess, because we do it so often, so I just say it in the flow. But yeah, please feel free to ask if there's any confusion anywhere. So coming back to interstellar medium, on the very left side you have a pulsar, right, which is radiating, and in between, so in between, what is, we have something called as scattering screen. Now what is scattering screen? Imagine all that material between you, so which is the observer on the right side, between you and the pulsar, you concentrate into this one screen. Now as this, so it becomes basically like a lens. Astronomy has a lot to do with optics, so study optics very well. Anyways, so so here's your pulsar, it's radiating, and when the signal interacts with the screen or with the lens, it gets scattered. All right, I'm having some very crazy winds here. Anyway, so it gets scattered, and you can see scattering in three ways. The size of the source becomes broad, or the pulses, they instead of being like sharp, they also become broad. And something called a scintillation, which is when you look at the dynamic spectra, which is if you look at the pulsar signal in frequency and time over a long period of time, you would see that the flux is changing over time. It's called scintillation. So so I'll show you what pulsar broadening looks like. Okay, so this figure, what you're seeing is, okay, so it's got multiple panels. Each panel is showing you pulse profile at a certain frequency. So the lowest frequency is on the top and the highest frequency is on the bottom. And you can clearly see the low frequency, the pulse profile is broad, and at high frequency, the pulse profile is narrow. So all these interstellar medium, they're frequency dependent, and they're very, very strong at a low frequency as compared to a higher frequency. So that's why I studied this source at very, very low frequencies, like below 100 megahertz. So yeah, so this helps us measure how the interstellar medium is interacting with the pulsar. So see, here's the proof. The interstellar medium, there is something there. It's not just empty. You can actually see the effects very, very clearly here. And then you try to fit it, and then you try to obtain the scattering parameters. But then there's a whole another level. But what I'm really trying to emphasize is, let's go back here. There are four main effects. One is the dispersion, which is the delay in the time. The second is the broadening. The source itself appears broadened. The next is pulse broadening. So you see low frequency profiles, they get broadened, the higher frequencies are narrow. And there's the variation in the flux. So they are so I talked about pulsar timing arrays, right? And I talked about how the period, or not the period, how the pulse arrival time from a pulsar gets affected because of gravitational waves. And there are many more effects which affect the pulsar timing arrays, but we don't have to get into detail here. So here's the summary. The summary is neutron stars, they come in various flavors. They come from radiation powered, or you have magnetars, you have millisecond pulsars. There's a range of sources. These sources being so exotic and being basically the next thing to black hole, they provide us a very interesting laboratory to explore. And we are still trying to understand what's going on there. We are still trying to understand the equation of state, and we are still looking for more sources. We don't know what we may find. And hopefully, I think the next discovery that we'll hear about would be a discovery of the gravitational waves from binary supermassive black holes. So any questions so far? All right, I guess I'll talk about my journey. So let's go to that. Okay. So yeah, so my life at IISER Pune. So I was undergrad at IISER Pune. And yeah, in my undergrad, I was mostly focused on coursework. I did a few semester projects with Dr. Ramana Athuria, which was, so one of them was basically on the imaging, learning few imaging techniques. And I think I did one semester project on very basics of Pulsar. So that's how I got introduced to Pulsar. Apart from that, I also went to, so with my friends, I also used to go to IUCA, I guess, just to get an idea of what astronomy is and how to get into it. And I also went to IIT Gandhinagar for a summer internship where I worked a little bit on gravitational waves. So yeah, in my undergrad, I basically tried to work on various small projects just to get an idea of what astronomy has, what kind of sources people work on, because it's a huge, huge field. So you really have to pick something in the end. So for my master's thesis, oh, by the way, this is my picture from the graduation. So with all my friends, I was very happy here. And yeah, so for my master's thesis, I went to Raman Research Institute. And I think that was a very, very good decision for me. So I got to work with Dr. Avinash Deshpande there. And yeah, so I remember when I went there, he just gave me this code, which is written in Fortran. And I'm like, this is a very huge code, and then like I had to like just learn through it myself and taught myself programming. I mean, I knew some programming before as well, but I didn't know Fortran. So in my experience, sorry about that, the wind is very strong here. In my experience, at least in astronomy, as your advisor changes, your programming language also might change. So be ready. I mean, so far, I mean, right now the trend is Python, but who knows? So yeah, so I went to Bangalore and I worked on pulsars. I worked on multi-frequency study of one specific pulsar, and I got to present my first poster at the Astronomical Society of India. So which was a very interesting experience. And then I began with my PhD application process, and I'm sure a lot of you who have already gone through it and who will be going through it, it's not an easy process. It can be a little unnerving, like you don't know what's going on, you don't know where to go. So yeah, so then I went for my PhD. So yeah, my PhD was a lot of fun, and PhDs can be very overwhelming and crazy. And in my experience, PhD is not just about like getting your work done. Yeah, you have to do that, but you also need to take care of yourself. You also need to get involved into other activities. So most of my work I started with the supermassive binary black hole system. So here's a picture of me with my advisor. So we got a lot of press for this. So this is, I think, this is a picture from some news outlets, I think. So anyways, so the funny story is I didn't really intend to work on supermassive binary black hole system. I think I was in my second year, and my advisor and I, we were still like figuring out what kind of projects I'm gonna do. So I think I was kind of waiting on some data to work on. But he was like, "Hey, I have some data. Do you want to work on this?" I was like, "Okay, what is it?" So he's like, "It's a data on black hole." I was like, "Okay, cool." And I ended up reducing the whole data, and then I'm like, "Okay, I'm seeing some stuff here." He's like, "Yeah, these are two supermassive black holes." I'm like, "Great." And then he gave me more data. It's like, okay, so here's data from like 10 years ago, and I put it all together, and then we found that there's some orbital motion between these two black holes, and then we wrote a paper. And yeah, it was a very fun experience, and a lot of crazy times too, because writing papers, especially like for the first time, it's a hard process. It's a process you learn over time. And then my main project was, of course, to work on pulsars, and I got a few papers out of that project, and I'm still working on pulsars. So apart from my PhD, I did various other things. I used to go to martial arts classes, but I stopped after a while. But it was fun, just to get a feel for what's different around. I started hiking a lot. I started running. I don't think I ever did any of these things when I was in India or in undergrad. I was mostly like, okay, here I have some courses, and maybe hang out with my friends. But I didn't really explore much in life, to be honest. But yeah, PhD definitely. I definitely explored a lot, and I took salsa lessons, and I even took a tennis class at my university because they let me take it. So I was like, cool, I'll take it. So yeah, it's been a very interesting journey so far. And what's next after PhD? So yeah, this was a very difficult time for me because after my PhD, I was not entirely sure if I still want to be in academia. I had a job offer for postdoc from Australia actually, but I decided to say no because I was writing my thesis and I was like, I don't know if I want to do this. I was kind of like burned out a little bit, and yeah, so I had to say no. I mean, they gave me like 2 weeks, and I was like, I can't do this. I can't take any job right now. And after which, what followed was, yeah, I did not have a job for like at least I think 6 months. So I wanted to take some time off for myself anyway because I went on like a long road trip. I wanted to like explore more. But what I realized something was the transition from PhD to industry was not at all easy. It was a very hard time. And then eventually I was like, okay, I'm gonna apply for postdoc, and I got this postdoc, so I'm happy. I really like my work right now. I've been working here for I think more than 5 months now, and it takes up it's It's a very demanding job, and we'll see how it goes. So thank you.
I have a slightly out of context question. How do you measure the magnetic fields of the pulsars?
I'm sorry, say it again, please.
How do you measure the magnetic fields of the pulsars?
Yeah. So you measure the magnetic field from the spin down. So magnetic field is actually proportional to the period and the change in the period. So assuming that your pulsar is spinning down, you can measure the period, and you need to wait at least for a few months to get a good spin down value. And then you take these two and you can measure the magnetic field of a pulsar. Yeah. And I see there's a question on how magnetars are formed. So yeah, actually we don't know. We don't quite know how magnetars are formed. We What we know is that they have very high magnetic field, and they are varying a lot. But so okay, so to add to this, recently, so I'm working on a source which is a magnetar, and we think it's only a few 100 years old. So this is a very very young source. Now we're trying to see if radio pulsars, like if magnetars eventually become radio pulsars, or they're just their own class. So yeah, we don't really know how magnetars are formed. Do they? I mean, they might form exactly the same way as neutrons, as like pulsars, but we don't have exact answer. Yeah.
Hi, Karishma. I had a question.
Yes.
Yeah, so it's a bit maybe slightly tangential. I wanted to ask you, so where does the pulsar timing arrays efforts sort of fit in with the next generation of gravitational wave detectors like LISA, Einstein telescope, the Artemis mission? So in that picture, where do you see the pulsar timing array sort of fit in, make its mark, or what do you see there?
Yeah. So good question. So Lisa would be okay. So I said pulsar timing array. They would try to detect gravitational waves from sources which have supermass, like masses of like few million to few billion solar masses. But Lisa would do more like intermediate range. So recently, I think LIGO detected a black hole with a mass of I think few hundred solar mass, so which is the start of intermediate range. And what Lisa aims to do is it will detect. So as I said, gravitational waves, they have this huge range of frequencies, and one of those frequencies is covered by LIGO, one of those will be covered by LISA, and one of those will be covered by pulsar timing arrays. So that's where it fits. And so far, they have not really detected it, but once they detect the nanohertz gravitational waves, uh, that would give a confirmation that these binary supermassive black holes actually merge, and they give rise to a bigger black hole. And I think this would help us understand the whole evolution process of how supermassive black holes form and how they interact with their galaxies, because the supermassive black holes, we don't quite understand how do they form. So I think that's the bigger picture.
So just to follow up, sorry,
Yeah.
I'm monopolizing your time. So another question that I just to follow this up, what timeline do you see for the detection? For example, like do you think SK is vital to these detections, or do you think with archival data, with existing telescopes, it's possible to make a detection in the next 3, 4, 5 years? So what do you think?
Yeah, I think pulsar timing arrays can detect something in next 5 years or maybe 10. I think they are very close. So what they are really trying to do is they are trying to look for more millisecond pulsars so that they have a bigger and bigger network of pulsars. And as the more bigger network they have, the more they can go down to a lower noise level. So yeah. So I think and about SKA, I mean, I don't know exactly when it's gonna start operating, but SKA can be very important, I think, if they can, help find more neutron stars and expand the numbers. And I think with SKA, I don't know how much it will help in the noise. So anything that helps in reducing the noise for pulsar timing arrays would help it, accelerate its discovery.
Thanks a lot.
Yep. So I have a few questions here. Let's see. So one is, why are pulsars only seen in radio? No, pulsars are not seen only in radio. So you see, that's where they got, that's where they were discovered first. Pulsars are seen in X-ray. Pulsars are seen in gamma rays, and pulsars are also seen, I think, in optical too. I think it's very hard to detect them in optical because they are so small. So and they're like far away, so it's very hard to detect. But whereas the other all these other observations, it's easier to see them. And also, like, all these high energy telescopes such as New Star, NICER, or gamma rays, they're all outside our outside Earth's atmosphere, so it helps a lot more to detect them. So yes, they don't definitely emit in radio, they emit in other sources. And somebody is asking me, where are you sitting right now? It's outdoors. Yeah, I'm actually, it's work from home, so I kind of got, it's very hard to work from home all the time. So yeah, I'm actually somewhere else. So that's why you're seeing all the crazy windy air. Anyways, so the next question is, how wide is the variability in the angle between the axis of rotation and magnetic axis stars? How does this angle affect, if at all, the physics of the system? That's a very interesting question. I think the variability can be anywhere between 0 to 90 degrees, because like, you have a star where this magnetic field and the rotation axis, they align, and the one where do not align at all, which is 190. And how does it affect the physics? I think one thing it would definitely affect is how do we detect them. And so if they are like somewhere in between, you see this pulse emission. But if they both align, I think you would not see pulse, you will see a continuous emission. And if they are 90 degrees, I think you would still see a pulse emission, because it'll go behind you. So I don't think it really affects the physics per se. Maybe a little bit, depending on how it's interacting, but I don't think it should affect how a neutron star in itself. So
Sorry
yes.
to disturb. Just as a follow-up, uh, so the angle. Sorry, continue. I'll just try to formulate my question better.
Okay. All right. So I have one more question, saying that how do we get information regarding the interior of neutron star? Yes, very good question. So there are various ways. One way is we try to look at the radiation, of course. So pulsars are highly variable. Like, not every pulsar, but a lot of pulsars are highly variable. So what you do is, so pulsars emit these pulses. Now these pulses from one another, they can be quite different. But if you average them together, you get a very stable profile. So one thing that astronomers do is they try to look at individual pulses, and they try to see how those pulses are changing over time, because that tells you something about the emission mechanism inside the pulsar. Another thing that people try to understand is they try to look at how a neutron star is cooling down over time. It's called something called as the cooling curves, and they have some, I think, but I think this is a very young field, so people still don't know exactly what's going on. But yeah, one way is, of course, the emission mechanism, and I think I didn't go into much detail. So for the X-ray emission, okay, so I said that the radio emission comes from these magnetic lines, and they're emitting these radiation. But for the X-ray, especially for magnetars, what we think is the polar area where you have the magnetic pole, what we think is it gets heats up, and because it gets so hot, it emits radiation in the X-ray. So that's something also allows us to talk about the surface. So yeah, so when we see all these different frequency, we try to map which part of the source it's coming from, and in that way we can tell if it's from the inside, we can tell something more about the surface. Will two binary in a pulsar system are stable, and will it be highly relativistic? Oh yeah, so this was a very big discovery. So I think it was 1993, I think. when Joe Taylor and was it Joe and Hurst Taylor? I might be confusing their names, but they found this relativistic binary system, and what they found was so these are these two neutron stars. Their orbit was decaying over time, and this was a big discovery because this gave a confirmation to Einstein's theory of general relativity, and for that they were actually given a Nobel Prize in 1993. So yes, they can be highly relativistic. It would just depend what the separation is, and if the orbit is decaying over time, they might get close together, and yeah, it will be very relativistic. Any more questions? Yeah.
As a follow-up to my previous question,
Yes.
do we, if we analyze the data of pulsars collected, do we actually see a lot of variation in the angle between the magnetic axis and the axis of rotation?
Oh, I don't think so. I think it can happen from like pulsar to pulsar, but so what people try to so the way people try to measure this angle is through the polarization, and I don't think they. I mean, it might wobble a little bit, because we try to explain a lot of like, sometimes we are seeing some kind of change in the pulse profile. We try to explain it through wobbling or of the magnetic axis, but per se, I don't think it really moves along a lot. Not something that I'm familiar with.
And from like one star to the other star, are there variations? A lot of variation in the data.
Yeah. I mean, it's like every pulsar is unique. I mean, they have some overlapping properties, but yeah, as the period is different, so can be there, like magnetic field can be different, and these are like just the basic properties, and if they are different, yeah, and it also depends on where the pulsar is. If it's in a binary system, yeah, you will see a lot of variation. If it's by itself, you'll see a lot of variation, or where in the galaxy it is. So it depends what are its surroundings, and a lot of factors can play a role in that.
Okay, thank you.
Sure. So yeah, so I have a question. What are the opportunities for students in non-academic fields after BSMS? Very good question. So my suggestion is explore. Like from my experience, so like a lot of people, they do PhD, and there's kind of like a trend, and after their PhD is done, they realize they don't want to be in academia. And as I said, PhD is not easy. It's a very it's very hard on you emotionally, and of course you have to work a lot as well. So I think it's good to explore. When you have the opportunity, work in various fields, get try to look for like internships, do internships, as many internships you can do, because I think they add up as experience. In fact, I think one should always take a break after they finish their undergrad for a year and explore more, and if they still want to do a PhD, then they should go for it, because that gives you a more perception of the real world. Otherwise, you are like undergrad, and you live in this cocoon. Everybody's doing science. Maybe the whole world is about science. It's really not. I mean, science is cool. I'm a scientist, but I think one should get an opportunity to explore. Any more questions? All right. I don't see any more questions. Feel free to ask anything. If you have any question about postdoc, PhD, or neutron stars, I'll be happy to answer them.
Okay, so if we don't have any more questions, I think we can end the talk here. Thank you so much, Karishma, for this wonderful talk. We really liked all the talk and the discussion also.
My pleasure. And yeah, please feel free to email me if you have any questions. Yeah. And thank you for inviting me.
Thank you.
All right. You guys have a good weekend. Bye.
Bye.